How do we evaluate this statement? Well, let's start off with the easy stuff. Let's think about evaluating just true, the value true. And why do we give it an E? E here is a map, and we'll get onto that in a minute, but it basically takes one value and maps it onto another. Now, if we evaluate true, well, we just get all the sets. S0, S1, S2, fine. Sort of boilerplate code. Now, let's actually start evaluating some of our statements. Let's evaluate for sum A true. So if we do eval of sum A, there exists an A true. Well, where is there an A transition? There is one in S0 here, A transition coming out of it, and also in S1 here, going into itself. So the answer for this is S0, S1. Now, how do we evaluate the bit with the X? Well, first of all, we must think of the ones that are trivially true. What does this mean? That means if you don't have a B transition, we just assume that you are true. Because what the square brackets mean is that for all. So if you don't have one to check, you're trivially true, right? For which ones don't we have a B transition? We don't have a B transition on S1 and on S2. We do have a B transition on S0, so that one actually has to be checked, right? So we have S1 and S2 trivially, but we could also have something else. We could have something else. So we do a union, which will make us, which will join the two sets together. Union on what? Now this is kind of the hard bit. We're going to write, where does this B transition come from? This B transition comes from S0, okay? So we're going to include S0 into our set if, and this is what this means, this little bar is going to give a conditional if. Now what's the destination? The destination is S2. So if S2, right, exists in E X, like that. Okay. We'll get onto that in a little bit. So this is the only the place where you're going to be using this E, this map notation, right? So let's carry on. What I'm going to write now is I'm going to say that L dash, or actually L prime, is equal to the inside of our statement, inside of this new X, this greatest fixed point. So I'm going to say that L prime is equal to A, true, and for all B, X. Now what we must do is we must evaluate this L prime with E. Now what does this mean? We must evaluate, first of all, this, and that's done in blue, this first bit, A, true. And we already have that. We've done it over here. Right, so S0, S1. And because it's an intersection, and so we must do the same, and BX. So actually what I'm going to write here is our recursive calls, and you can start to see why this is a recursive function. I'm just going to write eval again, so recursively calling the function eval bx with a map. This basically means when you evaluate this, you must then evaluate this, which goes over here, which then hits sort of a base case. Let's keep going. How do we do eval vxl prime, which is our final thing, right? We evaluate vx with the entire statement. Right, this is where we start actually doing our calculations. Now, this is the recursive part of the algorithm. We initialize an init value. The slides refer to it as Q0, but I'm going to refer to it as initial. It makes a bit more sense. And because it's the greatest fixed point, we add all of the states. S1, S0, S1, S2. We must also do, the slide says QC, but I'm going to say our new value, or our current value. Now our new value must be evaluated. So we must say eval, and this is going to be eval of L prime, the inside of this new X, with our map. And now this is actually where we declare this map. What is this map going to be? This map is going to take X, so it's the value X, and map it onto Q0, or our initial value, which is actually just all of the states. Now, how do we do this? Well, actually, before we've already evaluated L prime. I'm going to do this the evaluating step in purple. We've already done this, and this goes up here, right? Same thing, evaluate L prime. But now we actually have a map. A map actually works. So what is this? Eval L prime with an E, which is our map. So we get S0 and S1, but it's an intersection. So we must make sure that this also gives something in return. We must check what eval of bx is. Now eval of bx we've also done. So we go up here. Right, eval bx with E. So we get S1, S2. And this is the interesting part. We can also get S0. Right, we can also get S0 if S2 is in the set. Now, is S2 in our map? Let's check down here. S2 is right there. Okay. So S0 is included. So this step here, I'm going to draw it down here, is going to have our S0 because S2 is in the map right there. 0, S1, S2. This actually returns them all. So this means that going back down over here, this bit returns S0, S1, S2. So what is the intersection between S0, S1 and the set S0, S1, S2? Well, that means that this is just going to return S0 and S1 because it's the intersection. Remember, it's not the union. Okay, so the answer for our statement down here is going to be S0 and S1. Okay, we must keep going now though, because our initial value is not the same as our last value. What we do now in our recursive step is we change the initial value to be our new value, so our QC. So it's going to be S0, S1, because that's the answer that we just got. Now, we must also change this up a little bit so that the map now only includes our new initial value, which is S0, S1. So that's all correct. Now, let's evaluate this again. L prime. L prime was evaluated here. Remember, now we have a new map. Right, evaluate L prime. We get S0 and S1, right? Intersection, the evaluation of bx. Now, we got to go back up here again. Okay. We must go back there again. When we get S1, S2 union S0 if, right, remember, we get S0 if S2 is in the map. Is S2 in the map? It is not. S2 is not in the map. Therefore, we do not include S0 in this evaluation. So up here, what we're going to return is just S1 and S2. Great. So then going back down, the return from this evaluating step in orange is going to be S1, S2. Now, what is the union between S0 and S1, which is this statement here in blue, and the one in purple, which came from up here, which is S1 and S2. The only intersecting state is S1. That's what we return. And now we go back down to our eval step, so the return of this is S1. But we must keep going because our initial value is still not the same as our new value. So what I'm going to do is I'm going to change our initial value to be our new value, S1. And now I'm going to change our map once again to only include S1. Great. Now we must evaluate one last time. So let's evaluate. L prime. L prime is up, not up there, it is here. So we get S0, S1 if this intersection holds as well. We got to go back up again to evaluate bx. Right, bx, we get S1, S2 if S, and we also get S0 if L2 is in the set. Is L2 in the set? No, only S1 is in the map. Okay, not great, so we don't include this one. So the return from this is going to be once again S1, S2. Okay, done with that step. Now we've got to go jump back down. So S0 and S1 if the evaluation here, what's the evaluation? It's S1, S2. Okay, so we return S0, S1 intersection of S1 and S2, and once again, that is equal to S1. S1 is the only one that intersects them. So the answer here is S1. Now, the initial is equal to the new value, and the answer is S1, and we are done.